Welcome to our series on RAG, Retrieval Augmented Generation. We're experimenting with new ways to teach AI. First one is using popular storylines to make complex concepts stick. We really want to know, is this working for you? Whether it's too simple, too dense, or just right, your feedback helps us improve. Leave a comment with your thoughts, what works and what doesn't, or perhaps suggestions for future topics. If you find this helpful, don't forget to like and subscribe.
Hello, everyone, and welcome to this deep dive into the architecture of modern artificial intelligence. Today, we are exploring one of the most exciting and critical transitions in how AI systems function, the evolution of the RAG model, or Retrieval Augmented Generation. Our title, The Evolution of an AI Mind, encapsulates this journey, which moves fundamentally from a blind assembly line to what we are now calling a conscious architect. The image on the screen beautifully illustrates this journey. On the left, we see the traditional RAG, which operates along a simple, linear path, blindly following instructions. But as we move toward the right, the path becomes complex, incorporating loops and introspection, symbolized by the maze. The bright, intricate network on the far right represents the final state, the conscious RAG, or intelligent architect, capable of planning, self-correcting, and orchestrating complex tasks. This evolution is not merely a technical refinement. It is a fundamental shift in how large language models interact with knowledge, granting them a form of internal monologue and critical thinking. We will trace this path, understanding the limitations of the old ways and the revolutionary power of the new architectures that imbue AI with genuine intelligence. Our journey begins with the current standard, which we are calling the blind assembly line. This represents traditional, naive retrieval augmented generation. If you are familiar with RAG, you know it is designed to ground the large language model, or LLM, in external, up-to-date documents. However, standard RAG operates on a simple and rather dangerous fire-and-forget basis. Visualize a traditional assembly line in a factory. At Station A, we have the retriever, tasked only with grabbing documents based on a user's query. It acts as a blind robot, gathering parts. It then immediately passes these parts down the conveyor belt to Station B, the generator, which is the large language model itself. The critical flaw here is that the system implicitly assumes every piece of retrieved information is correct, relevant, and useful, much like an assembly line worker who never checks the quality of the component they are given before installing it. The retriever has no quality control, and the generator has no ability to question the input. This setup is inherently blind. This implicit trust in the retriever, despite the noise and complexity inherent in real-world data, creates a critical failure point that plagues all standard RAG applications. To understand the consequences of this blind faith, let's look at a clear analogy we call a toaster on the dashboard. This scenario perfectly illustrates the most common and damaging failure mode in naive RAG systems, the hallucination. Recall our assembly line. The user is querying for a part needed for a car, perhaps a steering component. In the scenario, however, Station A, the retriever, grabs a toaster. This is the irrelevant document, perhaps a document about kitchen appliances that happen to contain similar keywords to the car query. This piece of retrieved information is noise. In Step 2, the generator, Station B, receives the toaster component. True to its programming, it generates the car, but without question, it welds the irrelevant toaster directly onto the car's dashboard. The result is structurally nonsensical. In artificial intelligence terms, this result is a devastating hallucination. The LLM, relying completely on the irrelevant document, confidently produces a nonsensical, ungrounded answer. Crucially, because the traditional RAG system lacks any quality control or feedback loop, the model remains completely unaware of its severe error, presenting the faulty information with absolute confidence. This is the cost of blind, linear execution. The limitations of the linear assembly line led to the awakening, the realization that we must move from a linear path to a continuous feedback loop. This realization is the foundation of self-correcting and adaptive RAG. The image here shows the transformative change. We are introducing a new element into the pipeline, what we call the QC manager, or quality control manager, positioned between the retriever and the generator. This manager fundamentally changes the paradigm. The shift moves from a simple, retrieve, then generate linear pipeline to an adaptive loop consisting of retrieve, then grade, then decide, and finally generate. The key idea is that the flow does not simply move from left to right. Once the document is retrieved by Station A, it is intercepted by the QC manager. This manager scrutinizes the quality and relevance of the data. If the retrieved data is deemed bad, irrelevant, or insufficient, the system must possess the capability to send the data back or loop back and try the retrieval again, perhaps after modifying the original query. This capability to self-audit and self-correct is the fundamental starting point for creating a truly intelligent RAG architecture. This internal auditing process gives rise to self-RAG, or self-reflective retrieval augmented generation. This is the spark of the internal monologue within the AI system. Self-RAG introduces a metacognitive layer. Previously, the large language model simply answered the question based on the input it received. Now, with self-RAG, the LLM critically critiques its own entire process in real time. It is important to realize that the LLM is now operating in two modes. First, it functions as the generator, providing the answer, and second, it functions as the critic or the judge, evaluating the quality of the inputs and the outputs. The analogy here is profound. This is the system developing self-doubt. It's the first essential step towards true intelligence, as intelligence requires knowing when you do not know something or knowing when your data is insufficient. The key capability of self-RAG is that before committing to an action, the system now asks itself a series of critical, reflective questions. It acts as its own internal guardrail against the errors that caused the toaster on the dashboard incident. It pauses, reviews the materials, and evaluates the next step, ensuring higher accuracy and reliability. To formalize this new internal monologue, self-RAG focuses on the three questions of a self-aware system, essentially three critical decision points that elevate the system above blind execution. Decision 1 asks, do I need to retrieve? The problem with naive RAG is that it searches for absolutely everything, even simple conversational or common knowledge queries like, "Hi, how are you?" The fix in self-RAG is that the LLM first assesses the query. If it is conversational or clearly within its parametric knowledge, it skips the retrieval step entirely, saving crucial time and cost. Decision 2 asks, is this document relevant? This addresses the noise problem. Retrieved documents are often noisy or irrelevant. Imagine getting apple pie documents for an Apple Inc. Query. The fix is that the LLM grades each retrieved document, discarding the irrelevant ones before they can contaminate the final answer. This is a vital pre-generation quality check. Decision 3 asks, is this answer supported? This is the final safety net, addressing grounding. The problem is generating statements not backed by the source text, like saying revenue grew when the text says revenue was flat. The fix is that after generating the answer, the model self-checks if the statement is grounded in the provided context. If the model finds the answer is not supported, it rewrites the output, ensuring maximal faithfulness to the source data. This slide maps out the structure of the new consciousness in a flowchart we call the self-RAG decision tree. Unlike the rigid, linear flow of traditional RAG, self-RAG introduces sophisticated guardrails at every single step of the process. Let's trace the flow starting with the user query. The first decision point is retrieve. If the answer is no, we move directly to generate directly based on parametric knowledge. If yes, we retrieve docs. The second critical decision point is docs relevant? If no, meaning all documents are useless, the system does not give up. Instead, it enters a powerful loop, sending the flow back up to rewrite query and search again. This recursive step shows intelligence. The system realizes its initial understanding of the user's need may have been flawed. If the docs are relevant, we pass to generator. The final and most important guardrail is the third decision point, answer grounded. If the final answer is yes, we present the final output. If no, the model enters a recursive loop to regenerate the answer, utilizing the same documents but focusing on improving grounding. This ability to loop back and recurse, continually self-correcting if it fails a quality check, is what truly defines the intelligence of the self-RAG system. The mechanism that enables this quality check is a specialized component we refer to as the judge. This judge is how the system implements its inner voice and performs the metacognitive grading required for self-RAG. The judge is typically a smaller, faster large language model dedicated solely to serving as the quality control manager. It does not generate creative text. Its job is purely classification and evaluation. On the screen, we see an example of the grading prompt in action. We instruct the system with a specific identity. You are a relevance grader. If the document is related to the user question, output yes. Otherwise, output no. We then present it with a common mismatch. The user question is, how do I fix error 504? But the retrieved document is, the cafeteria menu for Tuesday is tacos. The judge immediately outputs no, classifying the document as irrelevant. This simple binary output has profound consequences. If all documents retrieved are graded no, the system intelligently assumes the original query itself was poor or ambiguous. It then asks a separate, generative LLM to rewrite the query. For example, it transforms the vague error 504 into the more specific gateway timeout fix and immediately tries the search again. This ability to diagnose the problem and fix the input, rather than simply moving forward with garbage data, is what defines self-RAG's vigilance. We now arrive at the pinnacle of RAG evolution, Agentic RAG, which we term the Autonomous Orchestrator. The leap from self-RAG to Agentic RAG is significant. Self-RAG is essentially a self-correcting writer, focused on refining a single answer based on internal critiques. An agent, however, is an autonomous manager. The fundamental shift is encapsulated in the new mandate. We no longer give the agent a rigid script or a step-by-step pipeline to follow. Instead, we give it a clear goal and a comprehensive toolbox. The agent is elevated from a follower to a leader. It dynamically plans and executes a multi-step strategy to reach the assigned goal. At every juncture, it decides which tool is the most appropriate to use, whether it needs to search the web, consult an internal database, or perform a calculation. This ability to proactively orchestrate a series of complex actions based on internal reasoning marks the transition from mere reaction to genuine, autonomous decision-making and planning. The architect's strategy relies on two core elements: a powerful toolbox and the cyclical cognitive process known as the RAG loop. The toolbox is a collection of specialized, external capabilities that the agent can call upon as needed. These tools extend the LLM's abilities far beyond pure text generation. We have the vector search tool for accessing internal company knowledge, the web search tool for accessing current, public information, the essential calculator or code interpreter for quantitative reasoning and solving mathematical or logical problems, and the SQL tool for querying highly structured data, like customer history. These are the agent's hands and eyes in the world. The second element, the RAG loop, is the agent's cognitive cycle for executing its plan, mimicking human reasoning. The loop begins with a thought where the agent asks, "What is my next logical step to solve the problem?" Based on this reasoning, it decides on an action, such as execute a tool with the right input. The tool returns an observation, which is the output, and the agent then processes this observation. Analyze the output from the tool. This cycle, thought, action, observation, repeats iteratively, potentially calling different tools each time until the overarching goal is fully achieved. This loop enables dynamic, complex problem solving. To truly appreciate the power of the agentic architecture, let's trace a concrete example of a quest in action. The user goal is ambitious. Compare the battery life of the iPhone 15 to the latest Samsung Galaxy and tell me which one lasts longer in percentage terms. Achieving this requires multiple steps and different tools. The agent starts with a thought: I need current specs. My internal data is old. I'll use the web search tool. Then executes the action, web search for the iPhone specs. The observation returns 20 hours video playback. The agent processes this, forming a new thought: got the iPhone data, now for Samsung. It executes the next action, searching for the Galaxy S24 specs. The observation returns 29 hours video playback. Now the agent shifts gears. Its final thought is, I have both numbers. Now I must calculate the percentage difference. I will use the calculator tool. The action is now calculator, executing the percentage difference formula. The final observation returns 45. This sequence of self-directed thoughts and tool orchestrations results in the final, quantified answer. The Samsung Galaxy S24 has a 45% longer battery life than the iPhone 15. The agent successfully broke down a complex goal into smaller, manageable, tool-assisted steps. This visualization brings the agentic control loop to life. We see the agent, the orchestrator, centrally located, its brain engaged in constant reasoning. This reasoning drives action. When the agent performs an action, it is fundamentally interacting with external tools, such as the web search tool, the database, or the calculator Python REPL. The output of that external action is then fed back to the agent as an observation. This observation then cycles back to inform the next round of reasoning. Crucially, the agent navigates to the answer dynamically. It is not following any single, predefined path. It determines the next step only after analyzing the observation from the previous step. For example, if a web search returns a calculation error, the subsequent reasoning will lead to an action using the calculator tool, not another web search. This fluid, adaptive navigation based on continuous feedback is the hallmark of the agentic control loop, and the reason why this architecture can solve far more complex problems than traditional models. One particularly specialized and highly valuable skill of Agentic RAG is its function as a smart router. A router agent's sole purpose is to classify the user's intent and direct the query to the single correct knowledge source, thereby avoiding unnecessary and costly searches across irrelevant databases. This capability is critical in enterprise environments where data is siloed. Consider two very different user questions about a stove. If the user says, "My stove is broken," the agent classifies this intent as a technical problem. It immediately routes the query to the technical manuals, which are stored efficiently in a vector database. Conversely, if the user asks, "Where is my stove?" the intent shifts to order tracking or logistics. The agent routes this query straight to the user order history, stored in the SQL database. It knows not to search the technical manuals for an order status. This sophisticated intent classification avoids searching irrelevant databases, dramatically increasing both the speed of the response and its ultimate accuracy, making the system highly efficient in complex data environments. Now that we have explored the immense power of advanced RAG, a pragmatic question arises. If advanced RAG is so powerful, why not simply use it for everything? The answer lies in the pragmatic return, understanding the cost of power. The fundamental trade-off is between latency versus reliability or complexity versus cost. Every cognitive step we have discussed in self-RAG and agentic RAG, every grade, decide, and thought, is an individual large language model call. And every LLM call adds cost and, more importantly, latency. As we move across the graph, we clearly see this trade-off. Naive RAG is the simplest and cheapest, requiring only one LLM call and taking about half a second. Self-RAG significantly boosts reliability by adding self-correction, but it requires around 3 LLM calls, increasing the latency to about 1.5 seconds. Finally, agentic RAG provides maximum complexity and reliability, but achieving that sophisticated planning and tool use demands 5 to 10 or more LLM calls, pushing the execution time into the range of 10 to 30 seconds. Organizations must therefore carefully weigh the mission requirements against the acceptable delay and the financial cost associated with complex autonomous reasoning. Ultimately, the decision comes down to choosing your champion and matching the architecture to the mission. There is no one-size-fits-all solution in RAG. The right tool for the job depends entirely on your specific use case. We can categorize the 3 architectures into 3 distinct personas. First, we have the soldier, which represents naive RAG. Its attributes are speed, directness, and efficiency. Its mission is simple: high-volume tasks where speed is critical, such as basic FAQ chatbots or simple summarization. Next, we have the Sentry, representing self-RAG. The Sentry's attributes are vigilance, reliability, and self-correction. Its mission involves high-stakes queries where accuracy is paramount, such as medical diagnostics, legal research assistance, or financial compliance checks. Finally, we have the Grandmaster, representing agentic RAG. Its attributes are strategic planning, power, and versatility. The Grandmaster is reserved for complex, multi-step problems that demand dynamic planning, external tool use, and sophisticated orchestration. such as advanced data analysis, software engineering agents, or complex logistical planning. By understanding the capabilities and the costs of each champion, you can strategically select the architecture that delivers the required reliability without incurring unnecessary complexity or latency for your specific task.